Introduction to Errors and Uncertainties. This video is part of a course on food physics, of which this belongs to the modeling section. It is the introductory first part, a very short one of a 5-part series on errors, uncertainty, and validation. So where are we in the modeling process? This slide just tries to orient us in that process. So this diagram shows the steps of modeling. So the first part is problem formulation, where we take a physical problem and simplify it with the governing equation and boundary conditions. That's our math equivalent of the physical problem. So that's problem formulation. Once we have formulated the problem, then we implement the model in a computational software or write our own software. Then once we start to get results, then we have to do validation and sensitivity analysis in relation to the model. This set of videos, 5 videos, relate to this part, validation and sensitivity analysis. And then once that is done, then we communicate the results of the model. So then this step is trying to build trust in the model. How do we make sure that the results, that the simulation results we're getting are indeed correct, reasonable? That's what these set of 5 videos are about. So this is the first and just the introductory video of the 5 that are in this series. So this is the one we're talking about. Here we simply introduce errors and uncertainties. That's all we'll do. The following video, this one, will talk about different types of errors and how we can reduce some of them. And then after that, then we'll get into reduction of one type of error, that is the discretization error. And this will be followed by estimating uncertainty. So how can we estimate the uncertainty of a model? And finally, we get to model validation, where we discuss how we can reduce the error and uncertainties in the model. Now, models have errors. Let's look at what we mean by errors. For this purpose, we choose a very simple process. So it's a canning process. So here, this is the canner in which we put cans filled with food inside, and then close the door and heat them up for sterilization. So let's look at a very simple product. So this is potatoes with some ground meat. So it's conduction heating. It's not being agitated. There's no fluid that we need to consider. As you can see, this one, and so it will just be conduction heating. So this is my reality of interest. Of this reality, we want to build a model. So the modeling process will lead to a mathematical model, and I'm showing one equation, just the heat conduction equation that gives us the temperature. Of course, if you're doing destruction of bacteria, which is the purpose of canning, we need an equation for that. And we want to keep track how much the nutrients are being destroyed, so we need an equation for that. So bunch of equations make up the mathematical model. In doing this, we make a whole bunch of assumptions. And it is those assumptions that we make very knowingly. We are really simplifying the reality. So, in other words, if we are simplifying the reality, we are making some errors. Now, once we have the equations of the mathematical model, like this one, quite often we cannot solve them exactly. So what we have to do is we build a computer model and solve these equations numerically. And in this numerical solution, again, we cannot solve these equations exactly. So again, we are making errors. So these are known errors that we are making. So the computer model will produce the simulation results that look like this, that may not be the same and is not the same as the reality of interest. And that means the solution here as compared to the reality of interest, it has at least these two types of errors that are shown here. One is the problem formulation error, or the mathematical uh, uh, model formulation error of the reality that's at this stage, and then the numerical error, as we say, in solving the model equations. Now, we can try to reduce them, but we cannot eliminate these results. It's very important to know how the model differs from reality always. This is why we need to validate the simulation results. We need to compare the simulation results that we get at this stage with reality, and typically that means we compare the simulation results with experiment. So models have errors, but models also have uncertainties, and these uncertainties are due to can be due to inherent variability. So let's look at that process again, where we have potatoes with some meat and some other material that could be in this can, and there is inherent variability, for example, in the physical properties of the potato. It's a biological material, so it's definitely it's going to have variability in the property. Then, we are doing a canning process, meaning we are modeling the destruction of the microbe. So the microbial kinetics that we are considering, that also the rate of that kinetics can also have variability, natural biological variability. So these variabilities are there most of the time. So these inherent, and they lead to these inherent uncertainties in our model predictions. So these inherent uncertainties need to be considered in the simulation results that we provide. So those are inherent uncertainty. We can also have uncertainty due to lack of knowledge, something we don't even know. Here we know, but there is variation in what we know. There is variability in what we know, but we can also have lack of knowledge uncertainty. So what can be an example of lack of knowledge uncertainty? So for example, does this potato material that we are treating as simple conduction, should we include multi-phase sort of uh, liquid vapor transport and liquid transport in various forms and so on, maybe with possible flows in the mixture? of this meat and potatoes. So all this complicated physics we are ignoring right now. We are just doing a conduction model. In other words, we may be making errors. Here we're not sure if we are making errors. Then another one could be, does the potato material get transformed so much that its material properties change in a drastic way? So those are some of the uncertainties that we have in the lack of knowledge. Note that it's something we do not know. That's what we're referring to as lack of knowledge, uncertainty. It's important to see that if we know some of these answers, that maybe we know that no, we really need to consider multi-phase um, uh, transport, but we choose not to, then we are simplifying it knowingly, and we are making physical approximation errors, as we discussed in the previous slide. So by uncertainty, we truly mean when there is lack of knowledge, meaning we just don't know any better. We do not know what is the real thing, so we could be making errors. This lack of knowledge uncertainty, also called epistemic uncertainty, refers to truly unknowns. We simply need to note these unknowns when we present our model simulations. There's nothing we can do, because if we know some other process is better, we may want to just do it that way. This inherent uncertainty, on the other hand, should be the inherent uncertainty, this one, should be estimated and reported whenever possible. To summarize this short introductory video, models have errors and models have uncertainties. We need to be aware of the errors and uncertainties, and we need to try to reduce the errors and uncertainties, and when it's not possible to reduce, we need to make notes of that. That is very important in a modeling process. The following videos will go into more details of these topics. So the very next one talks about the various types of errors and how we can reduce them. Then the next one goes into more details of one type of error, how we reduce discretization error and do what's called mesh convergence. Then we talk about some details of estimating uncertainty analysis, and finally we put everything together in model validation. That is how we can build trust in the model.